Okay, well, welcome to lecture 3. So as I was saying, we were getting started. These lectures are available on the Jupyter Hub system using that link that's on the home page. It's ugly looking, but what it does is it downloads and ensures that you've got the most up-to-date version of what's going on. You can download these lecture notes through the lectures folder online. I'll put those up. Of course, you have to then have Python installed in your own laptop, so this is a bit easier. Thanks for joining on Zoom. It's a nice way to hear my voice a bit more clearly, maybe through your headset. But even better is during the lecture, if you have a question, drop something into chat. If you don't have Zoom set up and you're like, I need to ask a question, use Kyle to help you ask that question. He's got a computer set up at the front that we can always use. Okay, so today what I want to do is talk more about how we write programs in Python, but specifically numerical programs. In our previous lecture, what we were doing, let's jump back to that for a moment. We were playing around with solving numerical problems, and specifically, we looked at something called a falling ball. And what we had done is we had written a program that had initialized some variables, namely where the ball starts from, how fast it's going down, starts at 0, and then we use an Euler algorithm to step through time to print it all out. And what I want to do today is take this basic program that we ended with, this sort of snapshot of how to write a Python program, and apply better programming structure to it. One of the things you can think about in this program is there's really two parts to it. There's the part which solves the numerical model. That is the one that sort of sets up the equation, solves it. And then there's a separate part to this program which displays the results and compares them to the analytical solution. It makes sense from a program structure to split these two parts of the program into sub-programs or modules or functions. So that's what I'm going to do here in lecture 3. This approach to splitting a function or a program into many parts is called a procedural approach, and that's the approach I'll be taking for Physics 2820. If you have taken a look at the textbook, you will see that the authors there are using what is called an object-oriented approach. That's very typical for a language like Java or C++. Python supports objects, but we won't be using them in 2820. Just one less thing we'll have to learn. There are lots of ways of writing programs, even more than just these two. As I said, my goal is to split our main program up into two parts, one that solves the numerical model and one that displays the results. So, do that. Let's write first the solving the numerical model piece of the code. The first task might be a piece of code that looks like this. So, falling ball model, it's going to take some arguments. One of the things that functions can do, besides having the def keyword, the name of the function, is you can put in 0 or more arguments or parameters that specify how this program is actually going to work. So what I've done is, rather than having them be variables inside the program, the variables dt, y naught, v naught, g, and then something representing the maximum time I want to run the program to are passed in as arguments. These are keyword arguments, and they all have default values. So it's very similar to what we had before when we had those values down here in this list. These variables are optional and could be passed in when we run this program. This is a bunch of documentation saying what this program is going to actually do, and then we have the actual program. And it's fairly simple. Since we've already defined a number of the variables, we want to have a counter for time. We want to initialize the position and the velocity. And then we go through this loop. And the loop, as we ended the last lecture with, we recognize the way to end this program is when the ball hits the ground. So as long as the position is bigger than 0, what will happen is the code will use the Euler algorithm to step through. So that is, it's solving an equation of motion, Newton's law, to figure out what the position at the next time step and the velocity of the next time step will be based on what it was in the previous time step all the way through. Time is being stepped forward by time steps dt. I'm adding this in there as a check to make sure this program doesn't go on forever. You can see in this structure that I can start at any height I want, right? I don't want to set this up in some way that I get in a situation where I'm in an infinite loop and I never break. By adding in a condition like this, what's called an if statement, and again, it's a block, structure statement, it's got an indent. If this condition is true, that is the current time is bigger than whatever I've set the maximum time to, what I want to do is break out of this loop. Stop doing it no matter what. It prevents the program from running forever. Once the program's completed, I'm going to take all of the stuff that this model produced. So stuff, not very technical word, but basically we'll take the time, the y, the v, and we'll even throw in all of the parameters we are passed in. So this chunk of data represents everything we want to know about the model. I'm formulating it as a Python dictionary, which is a common data type in Python. Basically what it does is it assigns keys and values. Using these curly brackets, what you're able to do is address this data structure and talk about model T or model Y or model V and get back the variable name, the variable value associated with any of those values. This model will return this dictionary as output to these functions. The idea of functions is they take in values, they do stuff, and they return some response. A function has an input and an output. So in this case, the output is the model values. It's everything we want to know about the model. You can run this model by just executing this function. So as long as you remember to first execute this program, shift, enter, I've executed it. When I run it, all the default values of the model are used, and this is its output. These are all of the entries in this dictionary. The model advanced to a time of 4.5299999948. It's a floating point number, remember. This is its final position, its final velocity, its initial position, velocity, its initial position, and then the parameters. If I specify keyword arguments, like saying, oh, you know what, I want to use this value for the time step, and I'd sure like to start with the ball being thrown up, as opposed to starting at an initial position of 0, it runs that same model, but now you've seen we've changed some of the parameters. In particular, notice the initial velocity is no longer 0, it's now 20. And so that means that the final velocity is not minus 44 meters per second. It's a bit less. Now it's a little bit weird. You got to figure this out. You're going, well, if I threw something up, shouldn't it be hitting the ground faster? Well, that's because this program only ran to a maximum of 5 seconds. If you throw a ball up into the air, it's going to be in the air longer. You need to change Tmax to have it hit the ground again. But the point here is what we're doing is we're able to change the arguments to this model. The second part of the code is to print out the results. So let's write a function that takes this data, this model as input, and spits it out as output. So this is a function, sometimes more known as a procedure because it doesn't return anything, it just does something. What it does is it takes as an argument all of the output from falling ball model. That is the previous program, it just takes everything. And what we're going to do is unpack it. These are the variables that are inside that dictionary. To address a member variable or a value in a dictionary, you use what is called the key and square brackets to look that up. So the model, which is this dictionary, has a bunch of keys, T, V, Y, DT, G, Tmax, and we can look up any of those values in any order we like. So now I know the values of T, Y, and V. Once I know T, Y, and V, I then can print out as statements, as strings, the final time, the numerical value, and I can use the initial conditions and the values that were passed into the model to calculate the analytical result. And so this was the same code as we had before. And what we've done is we've split the program now into two parts. The first part calculates the model, and the second part displays the results of the model, part 1 and part 2. Now, one of the things about functions are inputs and outputs that can be confusing is the name that you put right here does not need to be the same as the name you put right here. So this word model, whatever word I use right here, refers to the use of model here, and model here. When I call this function, what I'm doing is I'm putting something inside here that will represent model. I can put anything I want in. I can put in another variable, like the output right here. I could put in a dictionary. I could just copy and paste this entire thing. And I could put that right like that. That would be allowed. This whole thing is the model. It doesn't matter what I call it. This will become model inside this routine. So you can choose different variables for the inside of the function and the outside of the function, and that is just fine all the way through. Once we've split up a function to these two parts, we can put these two parts together to form an overall program, a master program, a driver program, or an application. Here is my example of an application. So what it does is it's going to compute the falling time for two balls if they're in two different gravitational fields. I might have some common parameters I use for both. I'm going to use one value of g for the first model. I'm going to add in a bit more print statements. I'm going to print out everything there is to know about that ball. And then I'm going to do it again, but for a different value of g. So let me run that to show you what you get. So this is a way where we were doing what's called code reuse. There's a principle in programming, a principle called the DRY principle, DRY, do not repeat yourself. So where you can, you try not to copy and paste code, you try to reuse the same code again and again. So this block of code produces this output, this block of code produces this output, and you can see that if gravity was weaker, if gravity wasn't 9.8 meters per second, then, and gravity was much smaller, of course, in the same amount of time, 5 seconds, it's going to fall a lot less. Or it won't fall nearly as fast going through. There was a question inside the chat from Kayla that says, the names in the parentheses must be set to the same data type. Sort of. Python's very loose. Some languages are very specific. If you create a programming language and you say this function will contain or takes in a floating point, you have to give it a floating point. Python, you can pass in any variable you want. There's no typing. So we don't actually define the data type of model, which allows you to write functions that take in lots of different things. So as an example of one of those kind of functions that can take in lots of different things would be this function right here, the print function. I can print a string and it works just fine to take in a number, but I can also print a number. And even though those are two different data types, print doesn't care. So you can use any data type you want in Python. Of course, when you go to actually use it, so if you write a program and I don't pass in a dictionary, this line is going to fail. So we can play with that. We can say, okay, I'm going to pass in not a dictionary, I'm going to pass in a number, and we'll see the kind of error we get. It says a type error, but that's not an error in the function. It's an error in this line that says, you passed in 42, and I don't know how to take 42 subscript t. I don't know what that means. So you do get errors, but they have nothing to do with the declaration of the function. So there are more general ways of doing it. So yeah, okay, so I'm going to delete those two statements. Okay, we can put them together. Here's a neat little bit of things you can do. Operations mathematically have definitions that are more than you would expect. We know that the star means multiplication. So if I take 34 and multiply it by a number, that means multiplication. Take a look at what we're doing right here. What do you think a hyphen multiplied by 34 might be? Well, of course, what it is, it's a string of 34 hyphens all put together. It's a very nice way of having to make this look good. I can just change this number as opposed to having to have a line that looks like that all the way through. So strings work together. Certain things make sense. Strings plus strings give you a new string. And of course, it doesn't make any sense at all to say a string plus a number. That's just nonsensical. Okay, so this way, or this paradigm of programming, procedurally breaking things up into steps, allows us to change the parts. We can reuse the same model code, but now do a graphical output as opposed to a textual output. So let me introduce a new function. Let's display the results as a plot as opposed to in text. So if this is a text way of displaying the output, like you can imagine it printing out on a typewriter, how could I do it with a plot or some graphics? So here is a piece of code that takes the same model dictionary as input, everything we want to know about the model. And it plots the falling ball at some, well, that's wrong, old comment. I'm just going to delete that because that was a thought I had later on. I apologize. But plots the falling ball simulation, the information about it. It does a similar thing. It extracts out the information. But now what we're going to do is we're going to make a plot. We're going to plot the time versus y for these two parameters. And then we compare it to the analytical result and plot that as well. Okay, because we are doing plotting, we have to remember to use matplotlib. Whenever you're bringing these functions, you have to import them. And I can show you what a plot looks like. Okay, so here we go. Here is a graphical representation of the same code base. This big blue circle represents the numerical solution. There on the axis is the position. There on the horizontal axis is time. And the red dot is the analytical one. This is an analytical representation of this paragraph right here. Now, I know what you're thinking. You're thinking a plot. Why can't I see the shape? Why can't I see the curve over time? At this point, and we will get to plotting curves very, very shortly, what we're doing is we're just making a graphical version of the same thing that falling ball results did. So falling ball results, all it did was create these lines right here. This information, that number, that number, that number, that number, that number, are being presented in this plot. It's doing that by plotting a dot right here, a circle right here, and a dot right here. The graphical library I'm using is matplotlib. Matplotlib, sort of most commonly used function, is a function called plit, because I import the library and get the short form of plt, and a function called command. What I need to do is have at minimum 2 arguments to this function, the value on the x-axis and the value on the y-axis, horizontal versus vertical. Horizontal one is the independent variable, always occurs first. And then you can proceed to annotate your plot or make it look however you like. So what I've done is I've gone and just said, I want to plot the time on the horizontal axis, y on the vertical axis. I want to make it a blue circle. I want my circle, which is called a marker, to be of size 14. And I want to associate a label with it. For my analytical solution, I'm going to make it a red dot. I'm going to make it a bit smaller, and I'm going to attach a label. These are all optional, and they let you play with how your plot will eventually look. Axis labels are defined using the functions xLabel and yLabel. That's what's making this text time ts and ym appear. What you do is you pass a string into those 2 functions. So there's time t. You're just passing in this string, and that makes that text appear. Please, anytime you make a plot, take the time to at least label the axes. It does help. As soon as you create a plot command, almost right away, add in the labels for the axis labels. If you provided labels to the data, then you can use the plit.legend command to have it draw a legend all the way through. Now, that is like a tiny bit of matplotlib code. There's lots still to learn. I'm not expecting you will learn all of it. You just need to know how to make the things that you want to make. If you've done the data camp exercises, you may have had some experience now to matplotlib. I'm going to draw your attention to 3 different resources that I think are useful for learning more about this graphing library. The first one is a set of lecture notes on Python in general, and NumPy and matplotlib for their use in science. They're called the SciPy lectures, and there's a chapter on matplotlib. So this is just one way of learning a little bit about what this library can do. It's not too long. It's basically just one web page. It talks about what matplotlib is. It's probably the most used Python package for 2D graphics. I agree with that. It includes this function called plit, or which is what we always call it. It gives you some examples on how to make a very simple plot. And then it starts talking about how you can manipulate that plot. So there's a plot. There's if you want to change the colors. Here's if you want to adjust the tick marks, basically the things along the sides, changing the widths, changing the colors, changing the limits. And relatively quickly, we get sort of the end of the page where we get a whole bunch of examples on different kind of plots we can make. So matplotlib is good at line plots. You can do scatter plots, pie charts, quiver plots, contour plots, filled plots, 3D plots, lots and lots of different options. So one way of exploring this thing is just to go through this tutorial and just try each and every one of these things. There's a number of different line styles, face styles, and symbols. So I went with big round circles and dots, but you can go with triangles or rectangles, pluses, X's, diamonds, whatever that trifoil thing is, pentagons, hexagons, lines. Those are all just letters that represent those basic shapes. And these markers can be connected. Matplotlib also supports lots of different color maps because you may want to play with the colors. So this is a good way of getting a quick one-go, one-page, read-through-it type introduction over and beyond the data camp exercises. The next thing I'll point you to in terms of how do I use matplotlib is think about the kind of plot you're trying to create and then try and find an example of that plot. So here's something called the matplotlib example library. What it is it's built into the documentation for matplotlib. And what you do is you go along and you try and find an example of a plot that you may want to do. And you may say, oh, okay, here we go. Here we go. I like this idea. There's 2 plots together. There's a plot over a plot. How do I do that? So we click on here and it gives you an example plot. And then it shows you some code for how to do that. It says, okay, if you wanted to make this exact plot, well, we need some data. That just makes the squiggles. And then this is how I do 2 plots. I use the subplots command. Subplots. So 2, 1. What that means is I've got 2 plots, one on top of the other. I talk about 2 sets of axes, axis 0 and axis 1, and I plot the 2 of them. I set the label for the bottom one, and I make it nice and tight together. So there's a nice example. You could modify this code to make this work. Anywhere in here, you can see I can just click on one of these options, and it'll go to the documentation right away. There are a few examples. So there are some basic ones. And then as we scroll down, matplotlib can do images, can do barcodes, can do quivers, can do contours. Scroll down. It's very good at doing plots inside of plots. It's good at doing plots beside plots. It's good doing plots of different sizes and shapes. It can do geographic projections. We can do plots that are all tight next to each other. We can do plots where there's color bars, plots where you do an inset of an area. Matplotlib can be used for statistics. Matplotlib can be used for pie charts. And you can annotate just about anything you want. So if you want to put the word spam or egg somewhere in there, there's an example. Notice that I'm just going along here, and we see lots of different options of how to do it. So the way that I do this is I browse through this thing until I find a plot going, that one, I want to make that plot. Well, that's how to make that plot. And then you modify all the way through. It's a good way of exploring what is possible, because sometimes you don't even know you could do that until you've seen it. Here's a cool one, right? Imagine you're doing something in statistics and you want to show the histogram in the two directions. How would you even set that up? Well, here's a little bit of code that gives you an example for something to follow. And we're only about halfway done this set of things. I'll draw you to this one, which is sort of cool. So we talk about a plot. There's a whole language associated with plots. Titles, ticks, labels, axes, the whole figure, the line. So there is sort of a useful map of all the things in Matplotlib. And the final one, which I don't know if this is important to you or not, but it might be. Does anyone follow or read this comic? In the chat, just give me a yes, somebody. It's got to be somebody. Kyle, do you read this? Kyle reads this. So for Kyle's benefit, if no one else's, point you this out. How to make an XKCD-like plot. Basically, all the way through, as long as you start your plot code with plit.xkcd, everything inside there is going to be as if it was drawn by Randall Munroe. No relation. I am not related to the guy. But, you know, that's just sort of neat. Comes in the package all the way through. So this gallery is a good way of explaining and showing and discovering what this kind of stuff can do. I'm still not at the end yet. Okay. If that did not satisfy you and you need more information, there's always the user guide. But I would consider this thing to be more like a reference. If you go to the user's guide, it goes on for a while in terms of how to actually do it, about all the details, and it goes into a lot of detail. The user guide is not the best way of learning the whole thing. The tutorials might be useful, but there's a lot of stuff in this library. Galleries and the sci-fi lectures are generally easier. Okay, all this is to say, take the time to play with Matplotlib. Remember that if you go to help, Matplotlib is a reference. Discover, try, attempt. If you want to make a plot that looks a certain way, try and figure it out. Always ask me a question if you want, but you probably can make it look with what you want. There was a question in the chat from Andrew. Are we going up to 2D in this course? We'll do more than 2D, but 2D is useful for printing out plots. It's the most common kind, but sometimes you want to be able to use 3D, or maybe you want to use contour plots, or maybe you want to use quiver plots. So these are all possible things. We want to plot anything we could get in Newtonian mechanics. So vectors, time contours, tracks in three-dimensional space, all fair game. Most of it will be 2D graphs, though. Okay, so that sidestep into Matplotlib allows us to make a plot like this, which is great. I can now make a different kind of plot. This plot is just what is the position at the end. Of course, it's always going to be near zero. A more interesting kind of plot might be what's the position dependent upon the time step of the model. So now I'm going to make a falling ball time step plot. The difference is it's almost the same, except for what we're going to put on the horizontal axis is not the time, but it's the time step. Well, I'll show you what that's going to look like. So now what I've done is I've plotted where the thing ended up, the end of the program. This is the difference between the numerical solution and the analytical solution. And rather than plotting time along the bottom, I've plotted the time step that we've actually used. Notice the 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. That's a logarithmic scale. Matplotlib comes with other plotting functionality, not just plots, but semi-log plots, or full log plots, semi-log Y plots, and a whole bunch of other ones. I can use that piece of functionality to write a program to examine how the time step affects the final position. So here we go. I'm putting together the pieces and reusing them. I'm going to use a for loop. I'm going to change the time step so it takes on each one of those values, 0.1, 0.01, 0.001, all the way up to 0.00001 in a loop. Every time I'll solve the model, and every time I will make this plot again and again and again, and then we'll run it. So if you take a look at that, this starts to be how we can use this information. So here is the final position after we run the program when we have a time step of 0.1, a time step of 0.01, 0.02, 0.001, and so on and so forth. Logarithmic scales typically go from smaller numbers to bigger numbers, so I flipped it around, and I figured that out by looking at basically an example in the Matplotlib gallery, so that I can see it thinking about the parameter of the time step increasing from left to right. And what you can see is, once you get to a time step of about 10 to the minus 5, there's very little difference between the analytical solution and the numerical solution. But this is a way of using these reusable components, functions, to have a program structure that lets you ask and be interested in more complicated questions. We talked about dictionaries at the beginning of the lecture. That is a data structure that lets you have key value pairs. This is a data structure called a list. Lists are used everywhere in Python. They're denoted by square brackets at the beginning, square brackets at the end, and then there's just stuff inside. The stuff can be anything. It can be numbers, it can be strings, it can be other lists, it can be dictionaries, and you can mix and match items inside of a list. What this construct is doing is saying, let D take the value of the first value, the second value, the third value, and so on as you go through. Lists are everywhere in Python. Okay, these are making static plots, as in this is a plot, I could right click on it and I could, so I can't do that. I could right click on it and I could say save image as, email image, I could send it to someone, I could put it in a report. It's a static publication quality plot. Because we're working in an interactive environment, we may want to work with this plot. Maybe we'll make it zoom in or zoom out or do something with it. The controls on the screen that allow you to interact with the program have this name widget. It's the sliders, the checkboxes, the menus of any application. They're commonly called widgets. So this thing over here, that's a widget. This drop-down box, this thing is a widget. These buttons are widgets. We can create widgets using Jupyter. There's a Python library. There's lots of libraries in Python called IPyWidgets, interactive Python widgets. And there's a specific function in there that makes any application interactive. What I'm going to do is I'm going to write a program, and this program is going to take an argument. The argument is how long to run the program for. So Tmax, if you remember back to how we wrote the model ran until the time exceeded Tmax or the ball hit the ground. Whatever those two things happened, that's when the program ended. So just to go back, scrolling up to the model, to the model, to the model. Here we go. Here is the model. The program will go until either the ball hits the ground or T exceeds Tmax, and then it stops. So this Tmax is a way of ending the program earlier, all the way through. Going down, going down, going down. Okay, so I'm going to pass that in as an argument to the overall program. The program is going to simulate it with that maximum one and then plot it. I'm using y-lim and x-lim. This is the leftmost one. This is the rightmost one. So it's not really upper limit, lower limit. It's left limit, right limit. Cassandra asked that question in the chat. Is the argument says for x-lim upper limit, lower limit? Well, it's left versus right. As before, as long as you hit down shift and then tab, it pops up and you can get the information. It's the bottom to the top one for x-lim. It's the left to the right. So depends which way you want to think of as advancing, going forward. But there's the documentation. It's the first or the second. X-lim by itself returns what the current values are all the way through. Okay, so. Or did I read that backwards? No, I read it correctly. The left and the right. Okay. Okay, but all this, let me show you how to use this. Interactive takes as its arguments. Interactive itself is a function. It takes your program with no curly brackets, and then you get to pass into it a range of values for Tmax. Tmax starts at 0, goes as big as 5, and has a steps of 0.1. Okay, here we go. Looks very similar to what we had before, but now we have this new widget. This widget lets me look at how the program is going to behave in time. So almost immediately, we have an interactive application. That is, this is telling me how long to run the simulation for, and it's plotting the analytical and numerical solutions at each point along this plot. So that's pretty cool. We got an animation. So what we can do is we can see the ball starts at the top, and over time, it falls down and down and down and down and down. Okay, that is one way of seeing the time history of what's going on. Take a look at IPy widgets for additional documentation. But this is something we can do. Let's kick it up a notch. Let's make this ball, when it hits the ground, not just stop, but bounce. I want to extend our model so that now it's a bouncing ball, an inelastic bouncing ball. So this is something we can model for first-year physics. We can make this model as general as we want, so I'm going to add in the new requirement that not a falling ball model, but a bouncing ball model still takes some parameters, but it has this new parameter, loss. What is loss? Loss is the fraction of energy to lose on each bounce. But just as before, I'll return a dictionary of all of the variables out so I can plot it. Here's the program. Same initialization, same basic loop. Falling balls and bouncing balls fall the same way. But we're going to add in this one little bit of code. And the one bit of code says, if the ball is below the floor, every time it does the step, it could go below the floor. If it's below the floor, then what I want you to do is calculate how much energy is in the ball. I'm going to assume that the ball has a mass of 1. Energy, kinetic energy for a ball is 1/2 mass times velocity squared. I'm going to calculate the kinetic energy, assuming that we lost a certain fraction of the energy. 1 minus 60%, you've reduced the amount of energy. Let's calculate the velocity now in this new case. Square root's always going to be a positive number, so that'll take an object which has been falling and make it start to rise. Of course, if it's below the ground, we need to sort of transport it up above the ground. This effectively is something that's going to lose energy, but it's going to preserve momentum in the system all the way through. Well, no, there's a force on it, so it's not an isolated system. Between the earth and the ball, preserves momentum. So this is a way of modeling the bounce. Same thing though, we'll stop when Tmax is exceeded, and then we'll return all the variables we need at the end of the day. Okay. Notice that we're using the numpy function square root. Because we're using numpy, you have to import the numpy library before you call the function. Going forward, we will put all of these import statements for matplotlib, for numpy, for ipywidgets, always at the beginning of a notebook to make sure you've done them. Okay, here is the bouncing ball model. What it does is it runs itself, and this is all the information. So after 5 seconds, it has a position of 4. If I want to understand what this model is doing, it might be nice to visualize it. So we'll do a very similar thing. We'll create a bouncing ball interactive app. That's just a name. What I'm saying is this is something that's going to compute where the bouncing ball is up to a time t, given by t equals 4, and I can use the exact same routine to plot it. I'm going to make sure that the axis labels aren't jumping around. I want them to stay the same, and I'm going to make it interactive. I'm going to let time go all the way up to, say, 20 seconds, all the way through. So here we go. There is the ball. I'm just defaulting to 4, but if I go back to 0, you can see the ball going to the bottom, and it hits the ground, and it bounces. And it goes up, but not as high because it's lost some energy, and it bounces. And it goes up, and it bounces, and it goes up, and it bounces, and it goes up, and it goes bounces. So that's sort of fun. You got a little bouncing ball animation going on. I have a question for you to think about. You see that we're plotting the analytical and the numerical solution. And as I go along, and I can either use my mouse, or if I click on that, I can use the right and left arrows on my keyboard. I can advance this through time. The step sizes are given by this 0.1 on the right-hand side. But notice that when I hit the ground and it bounces, the red dot disappears. And I've got a question for you to think about. Where does the red dot go? Why isn't the analytical solution appearing anymore? And how would we fix it? So hopefully you have an idea of what's going on there, but go through the code if you don't and try and figure out where's the red dot? Where'd my red dot go? How could I change this so I could still see the red dot? What would I have to change in the program? I'll just highlight that 3 times to make it clear. How could I make it so the red dot was still visible in the plot? Okay. Now, this approach, this way of doing interactive computing is sort of cute. I get a little animation. I can make a ball bounce up and down. Okay, well, that's sort of fine, but it's really inefficient. Every time we call interactive, every time we change this time, what we're doing is we're rerunning all of this code. So to simulate the ball going up to this point, I have to start it from up here and have it calculate all of these numbers and then just stop right here. If I advance it just a little bit to the right, the program has to go all the way back to the beginning and run all of this again to get to that same point. It would be far better if we could either store the results or do something so that every time we call this model, it retained the answer. So you could get a whole history of these things. One way of accomplishing that is to use something called iterators and things that are iterable. Now this is Python stuff, but I'll give you an example and it's not too bad. Rather than creating a model that's going to run to some end condition, I'm going to write a program like this. It's all basically the same stuff, same thing. I'm just going to change where it returns. If you remember in the old program, we ran the program, and then at the end, we returned what's called the state of the model, the values for the time, position, velocity, and all the parameters. Instead, what I'm going to do is inside this loop that goes on forever until it ends, until it breaks, right at the beginning, I'm going to package up all the variables and yield them back to the caller. A yield is basically the same as a return. It says, give me all this stuff and send it back to the calling program, whatever called this function. show it to you in use and it'll make more sense. If I run this thing called a bouncing ball stepper, and I give it some arguments, I get, oh, I guess I have to always run the code. What I get back is something that I'm going to call a generator. If you look at the type of this thing, it is a type generator. It's not a dictionary. It's this thing that I can iterate on. I can have it come to here and return this out at any time I want. To make it give it this first value back, yield the model results, what I do is I use the statement next. What next does is it runs the model up until the line yield, and then it returns whatever yield is returning, and then the program stops. So what next is doing is it's running this program from here all the way through to the yield, and then says, okay, that's it, I'm done for the moment. Next returns what, or gets whatever model is. Whatever this stuff is, that's what's returned. But because it's an iterator, something that is iterable, it can happen again and again, what I can do is have a second next statement. I can take that model and say, well, give me the next value of that model. And what this does is it jumps back into this code at this point, executes this line, this line, this line, this line, this line, all the way through the loop, through here, through here, through here, through here, through here, through here, and then yields again, returning the next step in the model. And so if I look at the next point, I get the next step in the model. So the first step was time 0. The second step is time 0.1, right? It's moved just a little bit. The velocity, the position hasn't changed at all because the initial velocity was 0. The velocity has gone from 0 to minus 0.98. It's accelerated a little bit going downwards. If I continue to go through these things, models are something that's iterable. We've seen something that's iterable before. Lists are iterable. Things that can go through again and again and again. So if I pass in a loop and I say for whatever variable I like in model, model is like a list. And it's a first thing, a second thing, a third thing. And so I can print it out. And what I get is the output from the first time, second time step, third time step, fourth time step, fifth time step, sixth, seventh, eighth, ninth, 10th, all the way through. Now, I only set this up to run for 10 time steps because I don't want to see a page of material, but that's what it does. The thing about a generator is once it has gone through its program, once it has done everything it's going to do, it has nothing more to give. A generator will spit out this value, then all of these values, and then nothing. So if I try and do that exact same line of code again, absolutely nothing happens because the model is done. There's nothing left in it. It's reached its end condition. The simulation has reached its end state. A new simulation requires the model to be created again, the generator to be created again. Okay, how to put this together into something cool. Some of you have begun to do the data camp exercises, which is great, totally optional, but encouraged. One of the things you may have encountered is reference to this library called Pandas. Pandas is known as the Python data analysis library, and it's one of the reasons Python is basically surpassing everything as the fastest growing language currently. Very, very useful to do analysis on lots of things, tied in very deeply with something called data science. Pandas can take a generator, a function which does this kind of thing, and figure out something called a data frame. So here we go. Pandas, the Python data analysis library, is almost always abbreviated PD. And if I have a generator, something that's going to step through my model, which is why I'm calling this thing a stepper, and I pass that into a data frame, what I've done is I've run this program again and again and again and again. Now ball is not just a dictionary for what the value is at one time, it's all of the data together. Ball is a data type called a data frame. You can look at the first few rows of it with head. You already see that we're getting some nice graphical way of displaying it. This is already prettier to look at than looking at it like this. Data frames are really nice because it's sort of giving you, like I can zoom in, I can do it. If I wanted to look at the entire structure, there's ball times it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's doing a smart thing. It says, there's like 2,000 rows. So how about I don't show you everything? Because you probably don't want to see 2,000 different rows. It's giving you information saying that this data frame is 2,000 lines long. It has 9 columns. The columns are all of the data, T, Y, and V, all the way through. Not only is there a head, but there's also a tail, the last 5 lines of a function. Now that we've got this data frame, what I can do with it is I can take any column from that data frame and plot it. I can take the T column and the Y column and make a plot. Plot T's on the horizontal, Y's in the vertical, label it, and show it. Now this show thing we haven't encountered before. Let's get rid of it and just explore what happens. I'm going to comment it out. You see this thing right here? You may recall in our last lecture I said that in Jupyter, the very last expression in any Jupyter cell is displayed. Well, the very last expression was plit.ylabel, and it returns this statement text. Because it's the last thing in the cell, Jupyter assumes I want to see it. I don't want to see it. I want to hide it. So there's a command that will just take the current plot that's being worked on and display it for you. Plit.show. Nice way of cleaning that up. But it's even better than this. There is the contour of our plot. This is the entire time history, Y versus T, of our bouncing ball. That's really what we're going for. That's the curve that shows you the evolution. The nice thing about a data frame is you can plot any column against any other column. I don't need to plot T. I could plot Y versus V. Y versus V if I wanted to. And there's the same model. What you're seeing is the model starts right here. It starts at a height of 100 meters, a velocity of 0. It accelerates downwards towards the bottom. When it hits y equals 0, it jumps. The velocity spontaneously changes from going downwards to upwards. Then it goes up into the air until it reaches its apex, falls back down, bounces up here. From there, jumps up to here, goes down here, bounces up to here, goes down here, bounces up to here. And I hope you can see that if you ran this long enough, eventually a bouncing inelastic ball would stop. Okay, so once we have a way of plotting, we can put this together and make a plotting routine and then an overall application. So this plotting routine takes in the information about a ball, the whole data set, everything that's been generated, and makes some nice pretty plot. And then I can run an application. I can advance this stepper forward in time all the way through, but I'm going to do it for 2 different energy loss rates. I'm going to run the first model for a loss rate of 40%, and the second time I'm going to run it for a loss rate of 60%. I'm going to plot both of these 2 things, and so we start to get sort of a cool little plot. 2 balls, one that's a bouncy ball and one that's a not so bouncy ball. This is the path going to be in time. So what we're doing is we're writing programs that lets us visualize things, lets us indicate different parts about the graph, and come up with some results all the way through. Okay, so that's most of the actual content that I wanted to get through today. I've got an exercise for us to work on, which you're more than welcome to work on right now for a little while. It will appear on assignment number 1, so take your choice. What I want us to do now to the rest of the lecture is I want to work on modeling a falling ball. Now this is the same thing we've been talking about. I've shown you how to model a bouncing ball. I want you to write code for a falling ball app. It's going to be very simple. It's going to go from here down to here and then stop, I assume. You'll need to create a new function called falling ball stepper. It'll look very similar to bouncing ball stepper, but have less lines. You're going to need a function called falling ball plot. But what I want this function to do is not only display the curve, I want you to also show me the analytical solution. So if the curve here will be the numerical solution, show me another curve, which is the analytical solution. Also plot that. So what you will have to figure out how to do is how am I going to calculate the analytical solution for all times? Make sure you've got labels and legends. And then in the assignment, you have to run this in a Jupyter notebook so I can see the output. The second part of the assignment question is to modify this falling ball app. So modify it, add an argument so that we can see dt. And what I want you to do is make it very similar to how we were doing these widgets. Here, you see how we were playing around with dt, time max. I want you to create a widget where this says dt, and so you can explore how the time step affects the error between the analytical solution and the numerical solution. With that newfound tool, the ability to play with how the error is affected by the time step, I want you to answer the following question. How much smaller does delta t, the time step, have to be to reduce the error in the numerical results by a factor of 2 for the same final time? So the idea here is you're looking at delta t, and there's going to be a difference between those two curves. How much will you have to shrink it by to reduce it by a factor of 2? How much would you have to reduce the error by to reduce it by a factor of 4? Now, to be able to make these things quantitative, you might need to also do something where you're not displaying just the curve, but you may want to look at the difference between those two curves. I'll let you sort of play around with that and figure it out. Okay, so that's lecture 3 in terms of this. I've taken this information, I've taken all of these exercises, and so what hopefully is working for you is if you jump over to your things, you should see a new notebook called assignment number 1. And assignment number 1 just has the 2 exercises we talked about yesterday, number 1 and number 2, and then this third one right here. My expectation is that your solution, both your code, your plots, any sentences you want to write, goes here, as in you could go to edit, where's add cells? Why am I dropping them? Select cells, move cells, insert cells. Oh, insert a cell below. There it is. It's right there. Why isn't there a right click? Why can't I add cells? I'm drawing a blank. I would look in the help usually if this was me, but we'll go this way. Plus sign. I can add as many ones as you want. You can add in my code, right? If you want it to be what's called markdown, okay, that's a code cell. To change it from a code cell to a markdown cell, up here you see the word code, to markdown. And now if you execute that cell, it all gets formatted. So typically notebooks are a combination of code cells and markdown cells. And you always can turn a code cell into a markdown cell, or a markdown cell into a code cell, however you like. There are shortcuts for doing all these kind of things. I tend to use shortcut keys that allow me to fairly quickly go between one kind of combination and the other. Please see the documentation if you want it. In terms of the assignment being available, let me just read through here. Okay, 2 questions about the assignment. Kayla asks, do we need to do this in the same notebook or in a new one labeled assignment number 1? Sorry, you're doing this in this notebook right here that's already labeled assignment number 1. So you're doing it in the same notebook that you all have. They're all separate. They're just blank. Whatever you put in here will stay as your stuff. If you do want to pull this off and you don't want to use this software to use it, course content on D2L, assignments, assignment number 1. Already posted. If you're using the Jupyter Hub server, you can just leave your assignment there and I can collect it. If you do choose to download this file, you'll have to reload it up under assignments, assignments, assignment folders, what used to be called Dropbox in U2L. Well, that's how I read them. I think on the student view, you see something else all the way through. But then they would pop in and you can submit as many as you want. In terms of a deadline or a due date, I'm gonna say a week from Sunday. I'll typically try to have them out on this Thursday and have them do a week and a bit later. I think I've counted my days right. So a week from this Sunday. And I'll say the evening, I think on the course online, I said 10 p.m. Anytime before 10 p.m. would be just fine, but try and make it work before that. Okay, are there any, in terms of textbook readings, we basically now worked our way through chapters 1 and chapters 2. Go ahead and take a look at it. Don't worry too much about the actual content, because most of it's Java and it's not relevant. I sort of done it all the way through here, but that's how far we've got. The data camp exercises are open. Thank you to those of you who've tried to do them. It is helpful to try and do these exercises before diving in and trying to do these things. Give them a shot sooner than later so you don't get into any issues. By my clock, it is just past 3 o'clock there. Is that right, Kyle? So Kyle and I are in the room for a while. If you want to talk to Kyle about any of these exercises, if you want to talk to me about any of these things, Kyle can turn off the speaker in the main room and the computer at the front is set up if you want to have a chat about just about anything. I'm not seeing any more chat questions, so I'm going to turn the video recording off and we will see you on Tuesday for our next lecture and our first lab, which will continue on. Thanks very much.